He'll start it off with some 10-minute or 15-minute introduction to ADS-CFT in the context of a 1D theory, 1 plus 1D theory. And then we'll take it from there. So this will be just following Suki's lecture on Mera.
Thank you. It's great to be back with you. I hope everybody is enjoying the workshop. So I'm going to tell you a bit more today about some aspects of doing DMRG with matrix product states. I guess I'll go ahead and show you my outline here on the next slide. And so I'll tell you a bit more about doing DMRG with matrix product states, but specifically about the kind of Hamiltonians that are most natural to use in this kind of DMRG. And then I'll tell you for about the rest of the time, about half the talk, about a method called METS, which is an acronym for these minimally entangled typical thermal states, and I'll explain more about that. It's a method for doing DMRG at finite temperature. But also, one reason I wanted to talk about it is that I believe this method should be fairly easy to extend to other kinds of tensor networks beyond one dimension. So it might be of interest to many of you who are looking at like 2D tensor networks. But then I wanted to start off today by answering some questions, or attempting to answer some questions that came up yesterday and also by email. So that's what the next few slides are about. So one question that came up, and I wish I could spend even more time on this, but unfortunately still it'll probably be a bit fast for some of you, but is what is this meaning of projecting the Hamiltonian into the local basis? So remember that you have a matrix product state, and you try to make almost all of the tensors out of unitary matrices. So that I only show those matrices here. And when you have these unitary tensors, you can think of them as forming a basis for a piece of the system. And if these tensors are made with the SVD, if you don't truncate, it's actually a perfect transformation from one basis, the lattice basis, to some other effective basis. If you do truncate, then it's not an exact mapping, it's like a partial mapping, it's like an isometry. So you actually leave out some of the states in the basis. But the idea is that when you're looking for the state. But just in terms of pictures, when we say local basis, what we mean is what these arrows are indicating here, which is these states that are labeled by these labels that are local to a particular site, or maybe a set of sites. So here I'm focusing on site 3, and the local basis would be the actual basis of site 3, and a label that labels the rest of the system going away from site 3. And those states labeled alpha here in this figure are a set of states that, if you don't truncate, then in this case, say for the case of spin and a half, the alphas would run from 1 to 4. And that would be some combination of all the original states of the lattice. If you do truncate, then the alpha would run from 1 to some smaller value, and that value is actually the m in DMRG, this number m, which is the number of states kept for the left half of the system. So that's what we mean. And I thought it would be helpful on the next slide to show you in kind of gory detail what this actually looks like, and hopefully this will also motivate you to be more interested in using tensor networks to do your calculations. So this is just an example for 3 sites. If we go ahead and contract these 2 unitaries together, we get some kind of unitary map that maps both of the first 2 spins into this alpha labeling. And so then we can see below what this looks like. So the idea is this tensor labeled H is the matrix elements of the Hamiltonian in the lattice basis. That's this gray tensor with the 3 indices on the top and bottom. And the labels are S1, S2, S3, and on the top, S1 through S3 primed. And then the U's act on S1 and S2, and then group those indices S1, S2, and map them to these states labeled by alpha. So you see that the result down in the lower right-hand corner is this tensor H tilde, which has these new labels, alpha and alpha prime, as well as the original S3, S3 prime labels. So, and again, you can see by the way the indices are grouped on the U's that it's like a matrix if you group the S1 and S2 together. Then it has the properties of a unitary matrix, or an isometry if you include truncation. So hopefully that clears some of that up. Also, just this morning I received a nice email from Himadri Varman, who I'd actually met before a couple of years ago in Mahabaleshwar. And so hi Himadri. And he asked me some nice questions, so I wanted to share these questions with everybody and attempt to answer them. Some of them are a bit outside of my expertise, but I thought I would give it my best shot. The first one is, why does this numerical renormalization group method that Ken Wilson first used, why does it succeed for the Kondo problem if it has this issue about treating boundary conditions too crudely. So it does have that issue, and so this slide is supposed to show you why it succeeds. And oh, sorry, I forgot to. Most of the talk I was pretty careful about not putting things in the corner, but some of it is covered up. But so the idea is that Wilson began his study by first mapping the I believe it was like a 2D or 3D Kondo problem to just a 1D chain, so it's an effective model for the Kondo problem. And at the left end of the chain, there's this impurity site. And then the way the mapping worked is that it gave something like a hopping model, except it's not a normal hopping model. It has these hopping strengths that decay exponentially quickly as you go away from the impurity site. And so, and this is discussed, by the way, in more detail in this nice PRL paper published this year, which connects this original method of Wilson to a matrix product state version of the same method. So it might be a nice read for those of you interested. But now if you please click on the slide, it shows how you can group the sites together in the NRG. And so in the NRG, the other day I showed it kind of blocking many sites all at once. But the way it was really done was that you first group the first two, find its energy eigenstates, then the next two. And you see that each time, the coupling that's coupling those sites to the rest of the system over to the right is relatively weak, down by a factor of lambda, or down by a factor of like 1 over lambda compared to the energy scales of the sites that are grouped. So even though you're neglecting that bond temporarily, it's not so bad compared to the overall energy scale. So this is just a special model that where somehow your real space position is also connected to your energy scale that you're considering. So that's basically, in a nutshell, the reason why this NRG method does succeed for this kind of chain. So then a related question was, just as in the NRG with the Kondo problem, can you use DMRG to produce RG flow diagrams? So can you study the flow of a Hamiltonian under DMRG, or kind of ask questions about flowing toward critical points or fixed points of RG, that kind of thing. So this is a really interesting question, and my short answer is no, but I only mean no in the sense that it's not usually done. But we know one case where it sort of could be done, which is this Kondo problem, which motivated the question, I believe. There you have, so DMRG is really a real space RG method, and in the Kondo problem, at least in its mapping, real space is tied to energy in the sense that I just showed, where you have energy scales corresponding to positions of your lattice. But that's not usually the case. Normally, real energy separations are not really visible in real space.
Miles, so I can interrupt before you proceed.
Yeah.
In the standard RG, we talk about renormalization of coupling constants.
Right.
So Berman's question maybe is related. Are there coupling constants here which renormalize, and are there flow for that? Okay, please proceed. Yeah.
Sure. So right. So basically, again, I think the answer is no on the face of it, in the sense that normally you don't have that sort of picture in DMRG. But I think it's an interesting possible area of future research, and I think that DMRG could be sort of a path toward coming up with such a method. So on the next couple of slides, I showed one way you approach this question. So the idea is that this may be known to some of you, and have already been mentioned in a talk, or maybe the one later today. So please, next slide. So the idea is that you can think of a matrix product state that has this kind of gauge, this particular gauge where most of the tensors are unitaries, as actually a kind of real space RG, where first you think of applying U1, and that sort of takes the basis for site 1 and transforms it into some kind of renormalized basis. Then you apply U2, then you apply U3. Each time you're grouping more sites together into some kind of renormalized basis. And finally, at the end, you have your wave function there at the top, which is psi 4. And then on the next slide, I show how in a different gauge, you can picture the RG scheme differently. So now you're grouping the left two sites together and the rightmost site 4 together as another effective basis. So I'm not the biggest expert on this picture, but it's sort of, the idea is it should be reminiscent of a mirror. It's saying that matrix product states are kind of like to gap systems as a mirror is to a critical system, only in a very loose sense. But the idea is that by taking this picture and developing it more, I think you actually could develop a real, more honest RG method. And the idea is that you would then take these unitaries and apply them to your Hamiltonian, and then if you study the resulting Hamiltonian, it might have the same form as your original Hamiltonian, but with different coupling constants to get back to to the question. And I should mention also that we're doing something already like this in a current paper that's on the archive, which is that we have mapped these fermion models that we're looking at with long-range interactions this way. And we can actually extract renormalized couplings that way. But it's not really DMRG, it's some kind of modified type of DMRG. And so then my final question, which I think is very relevant for yesterday's talk, is sort of getting to the question of why do we really need MPS-based DMRG? And so more specifically, does it really a different method from the traditional DMRG, and does it make a accurate calculations and lead to more efficiency, and also actually give kind of qualitatively new results that you couldn't get some other way? So basically, this is a kind of a subtle question, and other people might disagree with my answer. I'm sorry, but basically I would say the short answer is that for the ground state, that really traditional, if you just do DMRG for the ground state, either MPS language or using the traditional DMRG, basically not much. You get the same answer and the efficiency is basically the same. There might be mild differences. They are probably having more to do with the way you wrote the code more than the MPS versus traditional. And really you can map almost every step of the traditional code to an MPS code. You do get some actually important advantages when you consider excited states. And so this was pointed out by Sholok in his recent article about matrix product state DMRG. So the next slide is one way that you could use matrix product states to excited states more efficiently. So could you please click to the next slide? So excited states, the idea is, let's say you just used matrix product state DMRG to find the ground state of your hemorrhage. So you run DMRG, some number of sweeps, and you find the ground state. And let's call that size 0. It's cut off slightly, but call it size 0. Then the idea is that you can now form a new Hamiltonian, call it H1, which is your original Hamiltonian, plus some weight W, which you take to be, well, it depends, you have to sort of experiment with different weights, but just think of it as some number of order. And then you multiply this times this outer product of size 0 with itself. And the idea is that now if you consider the Hamiltonian H1, size 0 is no longer the ground state of this Hamiltonian because its energy is pushed up by this number W. And so the real ground state of H1 will be the next excited state up, assuming that W is chosen properly.
Question?
And so
but the second term, when you look in terms of as local Hamiltonian, it may not be sums of local Hamiltonians. The second piece may have very long range part.
Yes, absolutely. So this is not a traditional Hamiltonian that's local, but it's somehow this non-local piece that is very carefully, very specifically chosen here. So it's sort of any issues where you might worry about the ground state coming out being some kind of long range correlations. That we've had this method and it works quite well, actually. And so actually, you can kind of think of it as a canonical transformation of your H, in a sense. And so it's like
Professor Ramshesha has a comment. Please.
The question is that here the Hamiltonian is not optimized for the first excited state psi1.
Yes.
And all that you are doing is decreasing the Hamiltonian matrix that you earlier had, or push the lowest eigenvalue high in energy so that you get the second lowest eigenvalue.
Correct. Yeah.
But that is not the one that is actually optimized, or the density matrices are not constructed corresponding to psi1, so it is not really accurate.
Right. So my question was, see, all these approaches are well suited when you have total Hamiltonian, which is a sum of local Hamiltonians. Once you add this extra fellow.
No, but that is the same basis as the Hamiltonian basis. So
I see. So in the new basis, it may be very local. Yeah. Okay. Please go ahead. Yeah.
Oh, sure. So, so I didn't hear the entire comment. Is there a part I should respond to?
Okay. So
what I said was, this is actually meant for obtaining the second lowest eigenvalue of the Hamiltonian. Without is meant for obtaining the is meant for obtaining the second lowest eigenvalue of the Hamiltonian H, and it is not optimized for the state psi1. That is, the density matrix is, if I were to look at it as a DMRG method, the density matrix is not constructed for the state psi1 consistently, And so all that you are getting is the second lowest eigenvalue of the matrix H by a technique similar to deflation techniques.
Similar to?
Deflation. The matrix, you
I see.
To get the higher and higher eigenvalues, you can deflate it and get it, or project out the first one.
Okay.
Multiple targeting method where you try to combine two states into one density matrix to make the basis. But this method on the previous slide is different from that. And so the idea is that you can get the first excited state very accurately. And let me just say that the important fact on this slide is that you never actually form this sum, this H plus the W. You only imagine forming it. You never actually try to add the Hamiltonian to this outer product.
I see.
What you do is you just keep them separate, and when you do the eigensolver step in the DMRG, at that point you act each piece on your wave function, and then you add the result together. You don't ever add the Hamiltonians. That's just an important comment for those interested.
Okay.
So then the final part of this question that I wanted to mention is that the DMRG with matrix product states, I believe, has led to some very qualitatively new results that are that could be very important, and some of them are already in use. And this is just a short list of some of these results. So one of them that you may be familiar with is that Ian McCulloch, in a nice article that's published at this archive listing, showed how now the infinite density matrix, the infinite DMRG method, which was actually the original one, can be made to have a wave function acceleration scheme. And the only way to really see this is to use matrix product states. And so this is a very nice method. And then also, this matrix product states have led to a lot of nice schemes for doing real-time dynamics and finite temperature. Also, Steve and I have been working on a way to parallelize DMRG in real space, and so we're going to be publishing that soon. And that heavily uses matrix product states. And then also, you can combine DMRG with real space RG methods. So these are just some of the qualitative things you can get. Okay, good. So, so now today, getting into the talk, actually, I was going to tell you about matrix product operators, which are the Hamiltonians that you use when you're doing matrix product state DMRG. So the reason you need to use these kind of Hamiltonians is because just as you need to work locally with your wave function, you also need to work locally with your Hamiltonian. So you can see that if you tried to build this effective Hamiltonian and project it to a single site, if you use the entire Hamiltonian at once, there's too many indices. Basically, there's in-site indices exposed, and so the contraction will scale exponentially in the size of the system if you try to do this contraction. So the solution is to work with a different form of H. So if you please go to the next slide. So what you need is just as you try to work with a local form of your wave function, a matrix product state, you want to work with a local form of your Hamiltonian. So the next slide shows how this is an analogy with a matrix product state. Just as each piece of a matrix product state has a single site index, each piece of a matrix product operator has two site indices, so it's like a matrix itself, it's like an operator. And so it's just called a matrix product operator by analogy with a matrix product state. So then let me show you some examples of kind of simple, like elementary matrix product operators, and then we can work up to the more general type, and I'll show you how to construct them. So this is the most simple one, which is, it's almost too simple, and it's the identity operator, the many-body identity operator. And so each site just has one operator on it, which is factorized from all the others, and it's just the identity. So what do I mean by these lines being the identity? Well, a single line in this notation is actually representing a 2x2 matrix for the case of spin a half, or d by d for if you have your site dimension is d. So this line just means that if the two indices are the same, you get 1. And then if you click again, the two indices are different, you get 0. So that's all the line means. It just means make the two indices at the end of the lines the same. So now a less trivial example is to have a matrix product operator that represents an operator living on a single site. And so this operator on site 2 is just the matrix elements of some operator that you want to act on site 2. So if we take a specific example, we could pick this to be Sx, and then it would have these values. This tensor would have the values if you set 1 and 0 or 0 and 1, you get 1, otherwise you get 0. So that's all these tensors are saying. And then you can make even more interesting types of MPOs, which is to make a product of operators. So if you have a product of operators like this, so let me show you how you can combine them now to make an MPO. So please advance. So how do you actually make a Hamiltonian with these pieces? So one way that's actually kind of simple, but it's quite important, is that you can actually sum these pieces together. So if you have a Hamiltonian where you don't know how to make the NPO exactly, you can actually just take product NPO of this type and just add them up. And that's a good tensor code will provide us a method for adding them up. So for instance, in the iTensor library, we have a method that will do this for you. And so you can just make the Hamiltonian. But actually, I wanted to spend most of the time talking about how you can actually construct these Hamiltonians. So thinking the case, for instance, 1D Hamiltonians, but you can also do this for 2D Hamiltonians. The basic idea is that you want to look internally at the structure of one of these matrix product operators. And the thing we're going to exploit is that you can think of a matrix product operator as actually a Markov chain, which I don't have too much time to get into, but we'll see some of it. And this is explained in a paper by Crosswhite and Bacon, 2008. And so we'll see what this means in some examples in a minute. But the idea here is that we want to think of one of these rank 4 NPO tensors as actually a matrix of matrices, a matrix of operators. So rather than thinking of it as some generic rank 4 tensor for indices, we want to think first focusing on the left and right indices, then thinking about the top and bottom. So on the next slide, let me show you what I mean. So if we we think of indices first to the left, set them both equal to 1. So that's shown on the next slide. Then what that does is it selects the 1-1 element of this matrix of operators. So then we think of holding those fixed, and what's left is the 2 remaining free indices, and they now will, if we look at their elements, they will have the elements of the identity operator. So the next slide shows what it means. So it means if we set those indices at 1 on the diagonal, and then the off-diagonal elements are 0. So now another example from this same tensor, set the row to 2. So please advance. Then if we set the row to 2, and then the column to 1, so that means to set the left and right indices, then this 2, 1 of this of matrices, and in indices will give a Z operator. So if we look at the diagonal of that remaining piece, it has the elements of the SZ operator. That's what we mean by this notation. You think so setting the left and right, then you think of using the top and bottom indices. So with this intuition, you can actually build different Hamiltonians for 1D. So I'll show you an example of this. The example is the Ising chain. And the Ising chain just has products of SZ, SZ on neighboring sites. And so the convention here is lower triangular convention, which is we only set 4 triangles of these matrices of matrices to non-zero value. And we also use the convention that boundary conditions are such that we take the incoming index on the far left to be set to 3 always, and the outgoing one on the far right to be set to 1 always. So now let's see what we get. Setting the left most index 3 means that we begin by only looking on the 3rd row of the first tensor. And so on the 3rd row, we get a sum of 2 pieces, and the one return has this SZ operator. On site 1, we get SZ. And then that means that as we leave that tensor, we leave on the 2nd column, because you see the SZ is located in the 2nd column. So that means on the next tensor, we go to the 2nd row, and the only operator there is another SZ, and then that's on the 1st column. Finally, in the last tensor, we go to the 1st row, and we get the. And so that's one of the terms in our Hamiltonian. And so now on the next slide, we can see the other term, which is what if instead we take the term, which is to take on the 3rd row, and again, we start on the 3rd row because of that 3 on the left. Now that operates on the 3rd column. So we go on the next tensor again to the 3rd row. There we can pick up this SZ operator. That's on the 2nd column, and then we go to the 2nd row, and then we get a product of SZs now on the 2 sites. So the 2 terms that we get are shown here, and so those are actually, if you check more carefully, those are the only 2 terms that are non-zero. Hamiltonian is just the sum of these 2 terms, and that's the correct Hamiltonian for the Ising chain on the 3 sites. So now we can generalize more operators. So if you want to make the transverse field Ising, you just put these field terms, because they're on-site, put them in this lower left corner. And the way this works now, again, if we look at the terms we get, if we start on the 3rd row, we can start getting this field term in the first tensor, if you please advance. And we get the field term in the first tensor as one of our terms. it's on the first column, so we immediately go to the first row in the next tensor, and then we stay always on the first row and first column thereafter because of the structure of the matrices. So we just get identities for all the others. And so there's another term, if we get the identity on the first site, that's in the third column, so we go to the third row on the second one, and then we leave on the first column and then to the first row and get an identity. So again, we get, and then of course there's a third term that's not shown where we get the magnetic field on the last site. So that's how you can build complicated Hamiltonians. And so I just wanted to leave an example, is the MPO tensor for the Heisenberg. So this is where you would have an SU2 invariant model. And I'm not going to go through this example in detail, but I just want to show you how these could generalize. And so maybe as an exercise, you can go showing how this kind of matrix in it will give you the correct Heisenberg. You can see that it's really to the existing case, but now just have additional operators. Just as we have a pair of SZs, we also have a pair S plus S minus, another S minus S plus. And you see the couplings are there in the bottom. So that's all for that. So the reason this is really useful for doing DMRG with matrix product states is that it's got the local character that you need to be efficiently with your Hamiltonian. So the next slide shows that. So the idea is that we want to do a projection of H where we wrap it in our unitaries, or alternatively you can say isometries if we're doing truncation. And so we want to project a piece of our Hamiltonian into the local basis, in this case, the third site. And so the idea, first of all, you want to apply these tensors one at a time. If you try to apply them all at once, then the scale of your algorithm will be really. You need to apply them one at a time to get the m-cubed scaling that DMRG is supposed to have. So what you do is you apply the first unitary in contract, and then the tensors are going that way. Then you apply the second one in contract, and the tensors join, and keep going, applying them one at a time, and you see that what you're left with is an Hamiltonian where you've localized all the indices from the left over to site 3. And so now all the indices, all labels labeling the left side of the system equal now to site 3. And you repeat this to the right. Don't show it for the right side, but basically it looks the same. I should mention that the left slide here, the indices, these are the projected pieces of your Hamiltonian, and these are what you actually store in memory as you sweep back and forth doing the matrix products.
Miles, your voice is, there is some interruption. Will you please try to put your microphone and speak?
Sure, I can switch to my headset.
Exactly. Let's check that for a while. I do not know if it is due to that or due to internet.
Okay. So now I'm using my headset. Hopefully that will help with the sound.
Okay, let us check for 5 minutes. Yeah, please continue.
Okay, great. So now switch to different talk. So please, if there are any questions about matrix product operators, now would be the time.
Any questions? Okay, please proceed.
Okay, so now I'm going to telling you about this method for doing finite temperature simulations with DMRG. And this method goes by the name METS. And by the way, just to connect with the previous part, matrix product operators are actually very useful for this method, especially if you work with it in 2D. Though today I'll just tell you about using a different way of doing the method that doesn't use them, but just as a side comment. And so METS is an acronym that stands for minimally entangled typical thermal states. And this was come up by Steve White in 2009. And you can read about it in his Physical Review Letters article. But I'll tell you the details today. So just by way of introduction, this is a method for doing finite temperature simulations, and it's very efficient. It solves many of the efficiency issues that were present in attempts to do finite temperature DMRG. And it works actually a sampling method, the type of Monte Carlo method, but one that does not have a sign problem. And it samples finite temperature states that we call typical thermal states. And this method is described in detail in these two articles below. And these slides will be posted, so you can take down these citations later. But before I go into detail about the algorithm, I thought it would be helpful just to show you the basic steps of the algorithm. And so if anything seems confusing in the next few slides, please just wait, and I'll go through all this again in more detail. But basically, just to give you start, and here we're spin, but works for other kinds of models. And we're thinking like also of a 1D. So you start with products, And then you evolve this product state at imaginary time. And all that means is that you apply the operator e to the minus beta h over 2. And the over 2 is basically because this is a wave function. So that's like the square root of the density matrix. So you apply this operator, and I'll say more about how to do that. And then the next step is that once you've applied the operator, you now have some kind of entangled many-body state. And this state comes from a product state is called a METS. And I'll tell you also what it's called that. And once you have one of these METS, you can do interesting things with it. The most common thing is that you can just measure its properties. So for instance, you can compute an expectation value of an operator, say A, here on the third site, and then you can just and you can just store that number and keep it for later. And at the end of the algorithm, when you're done, if you average all those numbers, you get the correct thermal average as if you had calculated the entire density matrix. And so once you're done measuring all the quantities you want to measure on this state, you now have to get another product state to apply imaginary time evolution to. So to do that, you have to get it with the correct probability. So to do that, you actually collapse the wave function, just as in the sense of quantum mechanics, you collapse the wave function. And so I'll tell you how that works. But the next few slides just show a cartoon of that. You go site by site, just each time collapsing site into a product state and factorizing it over the rest of the wave function. And so then you obtain a different product state down to some finite temperature. So let's see how it works in detail now. So first, so unfortunately that's cut off, but you all know the Boltzmann distribution. So first, just a review of finite temperature physics. So the idea is we want to work in the canonical ensemble, which in the case of energy eigenstates, is a set of states with these weights that are nothing but the Boltzmann weights. And that's just e to the minus beta times the energy normalized by the partition function z. And then once you have these energy eigenstates, you do a sum over them with these weights, and you get the correct thermal average. And of course, in terms of the density matrix, where instead of having these C number weights, you just have an operator of the weights. But the advantage there is it lets you compute this trace over the thermal density matrix. You can think of computing that trace in any basis, not just in the basis of energy eigenstates. And by the way, this is an actual car that was parked in the parking lot of the UC Irvine campus, so I thought it was funny. It's the K-Log license plate. So, so now let's say we did have a way to actually work with energy eigenstates. The next slide says, let's imagine we had some kind of magical way to generate the energy eigenstates. I say magical because they're very hard to calculate in practice. And you could somehow generate time, and you'd be guaranteed that the relative probability of getting the next energy is e to the minus beta times its energy. And so if you see the set that I showed, there's actually some repetition that we got state twice, and we also got the second excited state twice. So it's like a Markov chain walk, random walk in the space of energy eigenstates. Once you do this random walk, if you do it long enough, if you take now these states which have come in and just do an expectation value average over these states, you get the correct thermal average, because the states are already distributed with the correct probabilities in your random walk. So this is just the idea of Markov chain Monte Carlo. But the problem is, and the slide discusses this, the energy eigenstates are a practical basis to use from Monte Carlo. So please advance to the next one. How is
sorry, there is some interruption.
Okay. Would it just help if I try to talk slower?
Please continue.
Sure. So hopefully the sound will improve.
Yes.
So saying it's not practical eigenstates as the basis for this method sampling, because of course it's very hard to find the energy eigenstates. If you could actually find them, then you would and you wouldn't need another method. So we don't have a method like that. What we have is another basis we could sample in, and that's what I'll be telling you about in the few slides. But the idea, we need to find some other ensemble to use. And actually there's many different ensembles you can use. The energy eigenstate ensemble. And the sufficient or necessary condition is that this ensemble set of states phi n, and let me point out these states can repeat. So the phi n's could actually all be the same, or they could be different. I'm sorry if you go back one. Then they're distributed with relative probability weights Pn, so that if you add up in this, if they add back up to the density at temperature beta, then, and that mentioned beta is 1 over T, if those of you who aren't familiar, then if you take an average in that ensemble, you get the correct thermal average. So there's a general recipe for making any thermal ensemble just from the basis. So let's say take any thermal basis labeled here by the states I, and it can really be any basis you like. To prepare a thermal ensemble from this basis, density matrix at temperature beta, and then cut it in half, just meaning square root times the square root. That's an exact thing you can do. And then you insert a resolution identity between, which just means a sum of the outer of I with I. And the reason you wanted to do this is to keep making everything look symmetric. So now the idea is that this product, please continue, this product you can phi tilde sub I. So if you think of acting e to the minus beta h over 2 onto the state I, then that product, let's call it phi tilde sub I. And we've basically made one of these thermal ensembles. And but the thing is, you have to normalize states. The states don't have to be orthogonal to each other, but they do have to be normalized. And normalizing actually gives you what these weights pi are. So at the end, the idea is that you normalize states, phi e to the minus beta h over 2 to your basis states I. You normalize them, and then once you normalize them, that gives you pi. And it's easy to show that if you sum up the outer products of the phi I weighted with the pi, it recovers for you the density matrix. So you've made one of these ensembles, and so the idea is now you want to sample the phi I with the relative probability pi. So you want to take a random walk in the space of the phi i's. And if you take expectation value, you're guaranteed to the right thermal average. But this is which basis I should we use to seed our, so we have to start from some to apply this time evolution to. And so there's basically, I'll give you on this slide and on the next slide, I'll give you two arguments that will lead us to the that we want to use. So one is thinking about entanglement. And so the idea is that in G methods, in matrix product state methods, the difficulty of working with state is growing with its entanglement. The more entanglement, then the more states you have to keep, and the larger matrices you have to work with. So to have the least entanglement that we can get away with. And so and it already has some entanglement, applying e to the minus beta h over to it only increases the entanglement in general. So we want to choose these states I to have as little entanglement as possible. That the entanglement, when it does increase, it will increase to some low value. And then the next intuition is a physical one, which said, think of taking our recipe for making this thermal ensemble and taking it all the way back to t goes to t. That's the same as saying beta equals 0. So that means that we actually don't do any imaginary time evolution at all. And so actually our thermal ensemble is nothing but the states I. And so intuitively at infinite temperature, we know that physics is totally classical at infinite temperature. And so the idea is we want to take these states to have some kind of classical properties. So we know that product states are actually that state. They have classical properties as much as we can make them. So the next slide says that's the to make. We want to choose the space to be the set of classical product states. And now, of course, that's not a... you can choose classical product states for a spin system in the z basis or in the x basis. Some basis, let's say the z basis, have the two properties we want. They're both classical, so and they have zero entanglement. And so all we mean is states that are factorized in every site. And so this leads us to the ensemble that we want to use, which is and that's where we use the recipe that I outlined, but we apply it to classical product state at infinite temperature. And so we make this product over 2 onto I, and then we normalize it, and we get phi I. And that state is called a state phi I. So if the entanglement of 0, the idea is that the entanglement in that I will not be 0 anymore, but we hope that it will be minimally entangled in some sense. It won't be entangled if we had made some other choice for and that actually does less be the case. Also, you can find working with these METs that they have nice properties that are intuitively correct for your system. So let's imagine a system of spin that has some kind of phase transition at temperature where you have spontaneous symmetry breaking. Because themselves break symmetries of the Hamiltonian, as you apply time evolution and go to lower and lower temperatures, once you phase transition, you'll actually see that the metals will break symmetries themselves. And so they have kind of intuitively physical properties that you would want. And so for this reason, this one is there that calls them entangled typical thermal states. So that's the meaning behind it. So please proceed. And so details of how do you really use on the computer, how do you actually calculate nets and work? And let me see how I'm doing on time. Okay, good. So Hamiltonians, you can take advantage of the Trotter decomposition. And so here I'm showing a higher order Trotter decomposition, but the idea is that we want to apply an imaginary time theta over 2, but we can break that up exactly as just steps tau, and then we can make an approximation, which is say, what if our Hamiltonian is actually a sum of terms? So the H1, H2 here are, we imagine there's an H3 all the way up to Hn minus 1, and so our Hamiltonian is actually just a sum of neighbor bonds. We can do the Trotter position, break our Hamiltonian into these gate operators. So that's shown on this. And so now we can take these gate operators, and if we take a small enough, then we get an approximation, and we can apply them one at a time to our matrix product state. So say we apply them on the first bond, then after we're done, we have to SVD the matrix product state, and when we SVD, we SVD to the right. And that way we've moved our amplitudes over to the next site, and now it's appropriate to apply the second bond, and we can do that again exactly. And what the approximation consists of, in the SVD, you always truncate, because you don't want the number of states in your matrix product state to grow indefinitely. You have to keep some limit on the number of states used. But still, you can, for a moderate number of states, you can basically. So now, at the end of the time evolution, many-body states, which is called the METs. And it's very interesting because not only can you, say, calculate the energy of the METs or calculate the magnetization on a given site and get these numbers, you can actually calculate lots of detailed properties at every site. And so here I'm showing an example of, this is the S equals 1 Heisenberg chain on 100 sites and only showing sites 20 through 80 in the bulk. The picture here is taken to be theta of t, which is basically pretty low, pretty resistant ground state physics, but you're not all the way to the ground state. And so here we show, first of all, I'd like you to focus on the green, red, and black curves. You see that they're very zigzaggy in the plot, and those are local magnetization on each site. And see that they have very rapid oscillations, and that's the male correlations that are present in this model. It's an anti-ferromagnetic nearest neighbor model. But then you see that these correlations have kind of characteristic correlation length. So for instance, in the middle of the plot, you see that there's a region where the correlation, where the spins are predominantly fluctuating in the direction, and the SX and SY components are small. But then as you go away from that region, over about a scale of maybe 20 lattice sites or so, you see that there's a twist in the order or in the magnetization, and you get predominantly fluctuations along the SY direction. You see that the energy fluctuates, and where the energy is low, the system looks like the ground state. I'm sorry, it's still on the previous. So when the energy is low, close to the ground state, which we know is a spin liquid for this model, so the magnetization is also small. And in those regions, the entropy shown in the upper left is also relatively high. So it's kind of neat to see the properties on finite nature in detail like this. So now,
excuse me, compared to the gap in this model, how small is the temperature?
Yes, good question. So,
equal to 10?
right, I should have written that. I think the gap, it's wrong, but I think the gap is of order 1. So I think you're, well, okay, I probably shouldn't speculate. I didn't check the numbers.
I was wondering whether it's nearly ground state or, okay, fine.
I know one way I can answer that, which is if you look at the bond energy plot, that number, -1, is quite close to the ground state. So you can see locally how the energy looks relative. So that you're really within a very tiny percentage of the ground state energy. So I believe this is already quite close to the ground state.
Ground state, okay. That's what Ramses is saying, that the ground state the bond energy is 0.4. Gap is 0.4. Okay.
Yeah, good.
Minus 1. Okay, please proceed. Yeah. So you are at low temperature. So temperature low compared to the gap.
That's right. So this is a pretty low temperature compared to the gap. Yeah. Yeah. Good. So thank you. So now this is to the last step of the algorithm. So we've already obtained one met. So we chose some kind of arbitrary state, and we push it down in temperature. So now the last step of the algorithm is to collect the function. And I wanted to go through this in detail. So this is a cartoon showing, if you have any state, there's lots of...
Miles, sorry for interruption. Since there is some break, we will test another method. Just wait for 1 minute.
Sure.
Please hold on. Please begin.
Okay.
Please, yeah.
Sure. So, this slide is that the final step of the Metz algorithm is the mounting, and those are the detail.
Okay.
So this is showing how you collapse the wave function. So the idea is that a Metz is actually an entangled many-body state, and these pictures are just trying to put that in a form that you have some kind of spin fluctuations. So the idea is we want to remove all those spin fluctuations and obtain a product state where there's no fluctuations and everything is site factorized. So the way the algorithm works is actually the algorithm works inductively. You just go one site at a time. And so it's easy to start on the first site because you have an edge. So sorry, could you please go back one slide? So on this slide, it's just showing that that you measure the probability. So here I'm considering the case of spin a half, just for simplicity, but it generalizes to any type of degree of freedom. So you measure these projectors. So here, one of them is the projector onto the state, which is just the outer product of the spin up state. The other is the product of the spin down state. Take the expectation value of these projectors on site 1, and those are probabilities that you can now use, and then the idea is you flip the coin. So if you click on the slide, it will flip the coin, and so you choose with this coin, weights come from those probabilities that you measure, you choose randomly which state that you're going to project into.
So we preferred $1.
Oh, is that? Oh,
sorry.
Yeah, so I saw for the web. I thought it might be fun to use a rupee coin, but I hope. So if you click, it will go to it'll flip the coin. And so the idea is that we randomly flip the coin and we get the up state. But we could have gotten the down state. We use a weighted coin, and the weights are coming from these probabilities that we already calculate. So finally...
sorry, I made some mistake.
So finally, this is the last step. When decided on a state to project into, the last step, number 3, is that you take this projection operator, which is that same outer product operator, to the site 1. Now we're forcing the system to be in the up state, so you apply this projection, and once you apply it, the system will factorize. And so now the final side of this is showing that you now have the system up state on site 1, and now it's disentangled from the rest of the wave function as a result. And you have to normalize this state before proceeding. But once you normalize it, now you see that the rest of the chain is disentangled from the first site, so you can just repeat this procedure. So and apply this procedure to every one at a time. The result is a new class product state. I call it I prime, and I don't show the proof here, but you can check that the probability of getting some particular I primed from the state phi I is given by this overlap, I primed overlap with phi, the square of that overlap. So that number is the probability that you'll get a particular product state I prime. And it's pretty easy to show by just going through the algorithm one by one. It's this probability, this transition probability, E goes from I to I prime, where I made your Metz out of, and I prime is the next classical product. That obeys this Markov chain fixed point condition. So you can show, it's basically a one-line calculation to show that if you, the PI, the probabilities of our METs, point of this kind of update. So this, by these collapses, guarantees that you get the correct thermal distribution of these METs. And that's an important fact. So now on the next slide, let me summarize the 3 steps of this algorithm just to kind of bring it all together. So again, the algorithm is you start from a product state labeled I, and then you generate an unnormalized METs phi tilde by applying this e to the minus beta h over 2 to it. Then you normalize the state. Once you normalize it, you have this state, and you can measure any observable you like, including the energy or magnetization or anything, any local observable you can measure, and you save those numbers, and then you are averaging those numbers at the end to get the thermal average. And then when you're done with that METs, you have to collapse it by that method I just showed, and that gives you a new product state automatically with this probability I prime overlap with phi I squared. And so that's guaranteed to give you the next METs with the correct probability. Good. So
question. So you keep repeating this for the same beta, right. And then once you converge, you go to another beta.
That's right, exactly. So you stay at the same beta, and then you you measure all the observables, and when you're done, you so I should make a few comments along these lines actually. So you save all these numbers, and when you're done, believe that you've reached convergence, which is something you can actually measure in the standard way by looking at autocorrelation effects and things. You can average all those numbers of an unweighted average, and that will the correct thermal average, that temperature beta. It's helpful. Different examples. For instance, if you work at infinite temperature, that basically means you skip step 1 because beta is 0. Mm-hmm. And so you're taking an average over many, many classical problems, and every time computing you're taking measurements in this basis of classical product states. So that's how temperature looks. And even though those states, they're very cheap to make, so it works in there. And if you go to the other extreme, which is beta to be very large, then every single METs will be the ground state. And I mean, I'm assuming there's a unique ground state, say. If that's the case, then every single METs will actually just be the ground state. You only need to do this once for that very large beta. So you do it once, and you find the ground state, and then you measure the observable, and then you're done, basically. You could do it again at that temperature, but you would just get the same number over and over again. So of course, you want to use DMRG, and that's a nice complementary method to this METs, and you can check the numbers match up as you go to low temperatures. So that's just a bit of a comment about how you would use it in practice.
So I just wanted to, I remember in other numerical methods, you keep applying this exponential Hamiltonian operator to reach the ground state. So now we were making use of things that comes on the way.
That's right.
In finding thermal properties. Okay. Just a loose comment here.
You're doing this projector method, but you're doing it very carefully.
Systematically and so on.
Divided by 2 factor is very important, of course. And
yeah,
so
exactly. I don't understand the meaning of 2. I will think about it. That will be one of the questions, I'm sure.
Sure,
right now we have a question from Kalyan.
Yes.
Is it compared to Monte Carlo method of doing the thermal calculations?
Miles, the question is how good it is compared to Monte Carlo methods of doing thermal physics for quantum systems?
I would say for 1D systems, it would probably be, extremely competitive, and would be especially nice because you get insight, I believe. First of all, you don't have to come up with any special estimators for measuring observables like in Monte Carlo, because every time you're getting a matrix product state, and there you can measure everything you want to measure, including things like entanglement. So you could ask some very interesting questions about the average entanglement of the METs ensemble, is other types of measures of finite temperature entanglement. So I feel like that's a very interesting future research project. For 2D, this method, really want to use this method for 2D in a problem where in a system where you don't have a time problem, because there quantum Monte Carlo probably beat it pretty well. But the idea is that this gives a way to do very efficient simulations of 2D methods where you do have a sign problem. And there, this is really one of the only few methods that can do controlled simulations.
One question. You made the statement that when beta is large, basically one operation, if you start with a good enough state I, will take you to the typical low temperature state.
Yes.
Have you looked at that wave function and seen how close it is to the actual ground states, for example?
Yes, we have. I don't have the numbers in front of me to say at what that.
But that's amazing because you start with the product.
But certainly we've seen that if you take beta large enough, you always reach the ground state, and that's.
I see. That's interesting because you start with some product state, and then one operation rotates you into the nearly ground state.
That's right. And so, if the product state is in, there are certain cases where if the state is chosen to be in the wrong quantum number sector, you do the evolution, preserves quantum numbers, then you can end up in a different state.
Sure. Like if you start with the ferromagnetic state.
Yes, that's right. And so if evolution was always trying to preserve quantum numbers, then it could go, you have to, so as long as kind of things, then you're good. Yes.
Thank you.
Right.
Please.
Sure. Good. And so to answer that question about beta over 2, we can go back later if we need to. But these slides, final slides here are showing some very interesting properties of this algorithm. So let me just mention and maybe do some more questions. So I really like this algorithm. I feel like it has a lot more potential to be really made much more powerful, and also to be used to learn some very interesting things about physics. So one of the possible ways to use it in a much more powerful way is this algorithm is what's known as embarrassingly parallel. And that's actually a technical term in computer science, this embarrassingly parallel term. And so what that means is that this algorithm can be made parallel in a completely trivial way. And so the way you do this is that, let's say you take some initial state and make your first Metz state, which is I call phi 1. Now you can do the collapse multiple times using a different random number generator, or just read a random number generator, and you get different product states called A, 2B, and 2C. So now you can distribute those product states to 3 different computers, and on those 3 computers you can now do the next step in parallel. And then you could keep doing this. You could always, and then from there on, these computers don't have to communicate whatsoever. So you could just keep generating states completely independently on those computers and just follow the numbers that you're measuring. And at the end, you just average all the numbers across the 3 computers to get the correct thermal average. So this was a perfect parallel speed up of this. So that's very nice if you have a lot of fact about this method. So please. And so the collapse, my favorite part of this method is actually the collapse part, because it's very interesting to think about. There's some other I didn't go into, but one nice thing is that you can do the collapse in different bases. So if you started your algorithm working, say, in the SZ basis, you could perform the collapse in the SF basis. And that would really help your algorithm by giving it a shorter autocorrelation time. But it's interesting to think if you took a single mini state and just collapsed it, then you'll get a different state every time. But those product states you get will have no correlation with each other whatsoever. And this is shown recently in detail by a nice preprint by Andy Ferris and Guy Vidal. I should have put Ferris's name also in this reference, so sorry about that. They showed that this is actually a useful method for working with Mira. So if you do this kind of collapse, you can do this to sample the properties of a ground state Mira. It actually has this, it's a type of perfect sampling where you're making perfect draws of product states from an angled mini-body state. So it's a really nice thing to do. And then a final feature of this algorithm is that it's very general. So if I explained the only part where I was actually working in 1D was when I was talking about doing the imaginary time evolution, and maybe a little bit about the collapse. But in general, you should be, many of the ways people optimize PEPs, for instance, Mira, is by using imaginary time evolution. And also this collapse algorithm to generalize to a tensor network, as long as it's a unitary type tensor network. So this method should generate 2D types of tensor networks fairly readily, and that's an interesting direction for somebody to explore. And also I wanted to show you some data and results in this method on the spin 1 chain. So not only can you make these nice pictures like I showed earlier, but you can get some serious data with this method. So what we did is each point we go to some temperature and work there, and then we loop over and over again until we get good convergence. It shows the magnetic susceptibility on the top slide, and then the specific heat on the bottom side. And this method has very high efficiency. At the bottom of the slide, I write the efficiency. The scaling of this method is like n, which is the size of your system, times m cubed, which is the familiar number of states cubed, as in DMRG, times beta, which is the inverse temperature. And so you see that the scaling is formally exactly the same as DMRG, as the finite DMRG, with this additional factor of beta. And so all you do is you have to work harder to go to lower temperatures. But of course, to go all the way to 0 temperature, you shouldn't use this method. You can just use DMRG. So it's actually really nice complementary method where you can get very good at higher temperatures, where also when you say that the n is smaller at higher temperatures. So it's a very nice method that way, very efficient. So now I wanted to, and I should point out also that here in these we were able to reach temperatures quite low, a beta of 50, where the gap is actually of order 1, just about like a half. And so see that you can see in the pictures, you can see the effects of the gap. You get this kind of exponential decay of the specific lowest temperatures. Okay, good. So now on the slide, I wanted to actually show some movies that are showing these METs, different. And Steve made these movies, and they're very nice ray tracing movies showing different METs for different systems. So hopefully we can now put those movies up.
Yes. Yes.
Okay.
Yeah.
Great. It looks good. So show sequences that are generated for the square lattice Heisenberg model in 2D. And so you see the nail, all the spins are anti-aligned with their neighbor, but there's significant thermal fluctuations. And this is J1, beta here is 10. And also the blue bars are showing expectation value of S dot S. So you can see that at this is already quite low, that the S dot S value. Okay, good.
So I have a question. In the movie, you see spins which are moving. Are they the intermediate factored states?
Oh, good question. So, those are actually the spin. So there are actually all those measurements themselves. So here the idea is that the temperature is not yet so low that the magnetization has really started going to 0.
So those spins are the values that you have actually measured.
That's right. Scale in that movie, so they could actually be small, but the idea is that they're still non-zero at this temperature, and they're all basically relatively the same size, which is why you can sort of see them all equally well.
Did you try to frustrate the system by putting a J2?
No, yeah, the movies, but actually the next movie is showing a geometrically frustrated system.
Okay.
So it's.
I see. Second movie.
Yeah.
We will go to that.
That was a nice segue into the second movie. Actually, that appears to be the third movie.
We have downloaded 3 movies. Mangal 3 நினைக்கல வெப்புக்கு போகும் இதில் போனால் சைட் அப்படி இருக்கு Sorry, we are downloading the second movie.
No problem.
We see the third
movie.
We
could first, actually. That'd be fine. So the third movie is just the low temperature Kagame, a chunk of the Kagame system.
Oh, I see. Okay, let's see that. We'll come back to second movie.
It's just, it's just 2 different temperatures. movie are basically the same thing. Different. So here, this is a beta of 20 for the j equals 1 nearest neighbor Kagame-Heisenberg model.
Okay.
And significant thermal fluctuations in the bonds because of see that the spins, because this is at low temperature, and you have frustration as well.
I see. So the weak bond denotes that basically there is no singlets across. Okay.
That's right. So the S value is higher on this.
So it's really resonating singlets.
Yes, that's right. So you see this actual resonating valence bond kind of physics here. It's some kind of completely unbiased numerical method. Still give kind of physics, which is nice.
And this is the size of your system, actual system.
That's right. This is and has open boundary conditions. So you can see that the bonds around the outside always sort of remain strong because they don't have any neighbors.
If you look at the spin values, can you see some wandering spin-ons in these pictures?
I did in that much detail.
Because I see some sites somewhere where every bond is weak. That means there may be an unpaired spin there.
Oh, right. Okay. So, or you mean a whole triangle that's weak, or just?
Or you take a given site. There are 4 bonds. So if all the 4 bonds are weak, that means there is a moment hanging there.
Right. Right.
Unpaired moment. Anyway, we can discuss.
Sure. But of course, if you take the base to be too large, the whole system is just going to, and its properties will be uniform.
Yes.
So, though there might be sort of virtual spin-ons there, you can see them.
Correct. Exactly. That's what I mean. Virtual spin-on.
So already this is a rather low temperature system. So maybe those are already kind of being suppressed.
So what is this temperature?
So this is a beta of 20, and this is with a j equals 1 for the spin half Kagame.
So beta is?
The beta is 20.
20. Okay.
But as you know, the gap is a small system, as Steve has showed recently, so it might not be that far below the gap.
Yeah. Okay. So the gap is very small here, right? It's supposed to be gapless for infinite system.
Well, that's sort of a matter of debate. But yes, gapless or else very, very.
Okay. So we will check for the second movie. No, yeah. Oh, sorry. The second movie is getting downloaded very slowly. Sure. So the second movie is at higher temperature.
That's right.
Okay.
So no problem. It looks quite similar. Basically, a greater fluctuation in the bonds, and then the spins are more. That's basically the difference with the other movie.
I see. What are the red lines? In some places you show red lines.
So, the red lines are just showing that the value of s dot s is actually positive on those.
Oh, I see.
It's negative on most of the blue bonds.
Okay, like ferromagnetic correlation.
Okay. Yeah, ferromagnetic on those bonds.
So any questions from the audience? Okay. So the second movie is getting downloaded, but you are saying it's very similar.
It's very similar. Actually, some of these slides look like similar to the second movie, those last few, just because you could see the spins more vividly and you could see stronger fluctuations. And so essentially the second just has more rapid fluctuation, or stronger fluctuations, and the spins are more readily visible because you're at a higher temperature.
Okay.
So that's all. So thank you.
So please proceed with your lecture. Is that the...
Great. So that's almost slide.
Okay.
I think I have a couple of slides just to thank the organizers and to thank both White, so Kieran support.
So
and that's all.
I'm sure there will be questions from the audience now. So we have about 10-15 minutes. The thermal thing that you described, that's very exciting. It was a pleasant surprise to me. So can you explain about this square root of Boltzmann factor?
Sure. So we'll go back to the slides that were showing the this recipe making ensemble, but with the chef.
Yes.
Where that is derived. Because by kind of quickly.
Yeah. So where should I
actually going forward now, the other direction?
Yeah. So yes. So this is yeah. Now it would be nice if you repeat this in the next 10 minutes quickly.
Sure. So actually,
next algorithm. Yeah.
I like this picture. This isn't a picture actually on the previous slide. This one cartoon here. This isn't my picture, but this is actually from the Viewpoint article in this physics magazine online.
Okay.
That was Steve's 2009 article. Okay. And this has a nice picture too. So you imagine at the very top of the figure you have these product states.
Yes.
And then you get this entangled state.
Yes.
And each of those you kind of add to your thermal ensemble, and then you're always measuring them and returning back to this kind of cloud of
right.
So that's a nice picture. Okay, so good. So on the next slide.
So in this picture, you have this big blue island. They say then you go to minimally entangled typical thermal states. What does that mean?
It might be a little confusing actually about the picture. So that blue island is just could be entanglement in the system.
Right.
It's sort of representing entanglement, in which you see it's localized to each spin up, and then it's across the system at the. Of course, it's not really long range, but you know, some kind of entanglement. And then I think so. It's not my but the arrow is just saying now include state in the set of previous states that we've already produced. So I don't think there's actually meant to be an operation there. It's just sort of saying that we logically included the previous ones.
Okay, let's go to your, there is a question. Shanai has a question for the previous.
Yeah, so when you say there's a step which says thermalize e to the minus beta h by 2. So that means that I just take the classical state and multiply the classical state, operate this e to the minus beta h by 2 on the classical state once, or do I do it many times?
Once.
Once. And then when you're done, you have one of these entangled states, and then you have to collapse a classical state, and then that operator again on the new classical state.
Oh, I see. And do e to the minus beta h by 2 on the collapse state again.
Yes, but this time it would be a classical, probably.
I see. Okay. Thanks.
Yes. Thank you.
Yeah.
Good. So we apply this always classical. And again, the details can be. I should mention that the only type I showed this talk for doing this operator was to apply these bond operators. But for Hamiltonian, you can also use a matrix product operator. So just as I showed earlier, you can make factorized types of operators. You can do this for this as well. And there's a lot of literature on how to make those. Unfortunately, it would take a lot of detail how to do it on this talk today. But you could operator for this e to the minus h over 2, actually.
So this is the first time you introduce e to the power of minus beta h over 2.
Right.
So you'll explain.
Explain where the 2 comes from, actually. And a few slides later. So did you want me to explain about the 2?
Yes, please.
Okay, so then these are steps. So if you would advance just maybe 3 more slides. Okay, good. So advance 2 more slides. 1 more slide. 1 more, please. Okay, good. So so you have to factorize your full density matrix into 2 pieces, and a factor of 2 is appearing. And so the reason you do this is because you can insert this complete set of states, and these states eventually these are that are going to be the product states, these i's. And so it's because now you get a nice symmetric factorization where once you think this operator onto the I, you symmetric decomposition of your density matrix. That's the idea. So
is the audience clear about it? No response from the audience. Okay. They are clear. Please go ahead.
Good. So this you take your density matrix and it as sum of outer products of other operators, other states. That's actually called a decomposition of the density matrix. So but to be a true decomposition, you have to normalize them. And so when you normalize them, the norms go underneath, and then you have to put the p in front, and so those weights. So you get one of these expanding your density matrix in a states. That's the idea.
And the intermediate state that occurs here is all states. You are resolving unity.
That's right, resolving unity. And so
when you do the actual operation, you pick up one product state, a typical product state. I see.
And then I just operate e to the minus beta h on that, collapse it, I will get a new state which is of the product state kind. I operate e to the minus beta h by 2 on that again.
Correct.
And keep doing this. And I simply take for any expectation value of any operator, I simply take the sum average of the expectation values on all these states I have generated by this, something like a Markov chain that I have generated.
Exactly.
That's
so, so that was the question. The question was, where did this beta h by 2 come?
So the beta h by 2, as I understand it, is simply taking, so what you're doing is you want to sample e to the minus beta h.
Correct.
So what you're doing is you're taking the square root of beta h.
Why?
Because you want to then go to these classical states. Because then the idea is if you introduce a factor.
That's what I want to, roughly see, but.
Right, so the idea is you want state. So if you don't do this factorization, always work with the operator. But by doing this factorization, it allows you to put in a resolution of the IDP. And now you have the decomposition in terms of some kind of states. So now to be able to sample over states rather than operator, that's why you need to put in this.
I see.
So each of these states, if you take the phi tilde states, phi I tilde states,
yes.
Each of them are now weighted with weight 1, if you like.
Yes, right.
So that's why you are able to then just generate those states by just running e to the minus beta h, classically collapsing it again, and then running it, and then therefore you'll be actually sampling that new kind of probability distribution which is uniform.
So let me now. Let me suppose I work in microcanonical ensemble. That means my density matrix, my averaging will involve sum over all this bra and ket corresponding to the constant energy.
Yes, right.
So that's what you are doing. So you work in a canonical ensemble because of Boltzmann factor, but you rewrite it as if you are working in a microcanonical ensemble because the sum of phi i's will typically belong to the same energy.
That's right.
Am I understanding it correctly?
That's a very helpful perspective, I think. Yes. So, like you said, it's not exactly the case because there will be fluctuations in the energy. So as you make beta to be larger, those will, or unless generally for larger beta away from transitions.
Because this taking square root is always fascinating. Dirac did it, and he discovered antiparticles and so on.
Yes.
So.
Yeah, I like that.
Can I just
reasonably clear? So follow up on that previous question to say that the weights of the phi tilde weights are 1 here, but the thing that you're really sampling with, the thing is that normalize them. When you're putting the norms underneath, and the p's appear on top. Now those are actually the weights. But the thing is, those weights you sample, and when you the part of the algorithm is automatically giving you the next state with the correct probability weight of p, this pi. So that's why when you compute an average, you take an unweighted average because the probabilities were taken care of for you in this sampling. And so in principle, for instance, you could actually get the same twice or more than once. So the probabilities already are taken care of for you. Yes.
So Shanai has a question.
So I guess a sort of a different way to look at what Pascal is asking is, suppose instead of dividing it by 2, I make it as beta times alpha h, alpha is some number between 0 and 1, and beta times 1 minus alpha h on this side. Then you don't have the advantage that the two, the states that you get by acting e to the minus beta h, the bras and kets are the same. You don't have that advantage. So 2 actually gives you the advantage that both these states turn out to be the same. So that's
absolutely. Yeah. And so you can think of this outer product as being like an expectation value that's waiting, basically. So when you take the expectation value, it's similar to taking the trace. And the trace will take these out product facing outward and wrap them around, and now they'll be facing inward. It's something like an expectation value. So you're right. Decompose symmetrically like this, and instead if you did this kind of asymmetric one, you would have one state on the left, different state on the right when you do the expectation value. And that's interesting to think about. I mean, there might be another variant of the algorithm where it's actually advantageous to do that. But how you generate the next state is not really clear to me, how you make the collapse part work the next state. But there probably might lead to some very nice new outputs. Mm-hmm.
So just one comment. If you choose the intermediate state, when you resolve unity, I as really eigenstates of the Hamiltonian,
yes,
then the separation into e to the power of minus, you can do it in any way you like.
That's right. Absolutely.
Yeah.
Mm-hmm.
That's where.
Maybe that would be a good case to think about to come up with a more general version of the algorithm. Mm-hmm.
Okay. So how exactly you do the operation? You explained it, I believe, but maybe you can repeat it.
Sure.
How do you evaluate that?
Yes, of e to the minus beta h over 2?
Yes, exactly.
Okay, so the example I showed occurs in just about 3 or 4 more slides from here. That example is just the example for a nearest neighbor Hamiltonian. So again, you can do this for more general Hamiltonians, and there you have to do it with matrix product operators or some other.
Am I going in the right direction? How do you?
So fast. I probably should have written a couple more lines, but the idea is, let's think of a Hamiltonian where you can write the Hamiltonian as a sum of operators. So a simple example, spin chain with nearest neighbor interactions. And so H1 would be the term S dot S connect spin 1 to spin 2, H2 dot S3, and there'd be H3, S3, S4. And so this is, I'm thinking of with nearest neighbor interactions. And so take beta over 2, and you can chop it into even smaller pieces. And so tau would be, some small number less than 1, 0.1 or something. And the idea, if you is this way, you're making errors of order tau cubed. So you tau small enough, you have a controlled way to factorize this operator e to the minus beta over 2, first into pieces of size tau, and then you also can factorize it in space in this way. Only making small errors as shown. So then once you have this, we call these gates, these e to the minus tau h sub each bond in, you take these gates and you apply them one time, and once you're done, that's like applying one amount of time step tau. And if you do, then once you're done with that, if you go enough time steps, you apply the full e to the minus beta over 2. So applying one gate means apply the operator, and again, on this side, you can see that that's a pretty small local operation. So this is just a 4x4 matrix, basically, and you're applying it onto sites, and that again kind of small matrix with maybe dimension 4 by m. And you can do that using a nice code. Any code that you can work with these tensors conveniently, you can do this. You can apply this gate exactly. So there's no error at that point. So once you apply the gate, it's sort of, you can think of it as fusing these two tensors together, and you just get a single tensor now in that one bond. So if you'd please advance, it'll show that single tensor. So that gate will kind of join the tensors together, but then to bring it back into this standard form, and at that point you have the option of moving where the, we call it the orthogonality center, but it's this location of these amplitudes. You can move it to a nearby site. And that you can ignore all the other sites because they're unitary, and you can just apply the gate locally near where these amplitudes are located. And then in this way, you move through the system in a sweeping-like pattern. It's actually very similar to doing real-time DMRG. You're just using a different kind of gate. And so each time you SVD and you truncate also to control growth of your bond dimension.
Okay.
Hopefully that
One more question. Yeah. Can you, the mic, Kurma?
How is it different from Chiang's algorithm for finite temperature DMRG that we had about a decade back?
Oh, let's see. So, very familiar with these other methods, but was that method, am I right, that it's taking some idea of transfer matrices? Is that the method? Okay. So I probably, you should take my comments with a grain of salt because I haven't recently looked at that method, but my belief is that that method works well, but it's sort of not maybe as wide. So it might be that you're limited, first of all, to one. Also, it might be harder to use it on more general kinds of Hamiltonians, like maybe actions and with, so really this is a very generic algorithm. You can use it in any kind of system where you can like make an MPO, for instance, for Hamiltonian. You can make this algorithm work as well. You can also make this Metz 2D. And finally, the scaling of Metz is quite similar to the scaling of ground state DMRG. And in fact, it can be much better in certain cases. So I'm not sure what the scale of Zhang's algorithm is, but it would be interesting to compare those to.
Are there any other questions from the audience?
I should make a follow-up comment. So if you're from a paper that Steve wrote a few years before, they came up with a method together with Adrian Feiglin, and this method is called the ANS method. Basically, you the entire e to the minus beta h over 2 operator in one shot. And so if you're familiar with that method, Metz is kind of like a descendant of that method. But the ANSERA method scaled to the 6th power, so it really doesn't scale very well. Metz scales as only m to the cubed power. So really, Metz is almost as well as you can do because it's the same scaling as DMRG itself.
Okay. So if I think there are no further questions, so we will think about what you have told us today, and we will have discussions in the afternoon, and we will communicate with you through email. So it's really a great pleasure to thank you for taking these extra efforts to come to the office and this late hour and enlightening us with these 2 nice talks.
Thank you.
So it would have been much better if you were with us. But so in fact, just to make you feel bad, today afternoon we are going to the beach. And but we will talk about what you told us.
Great. I put this picture because the boats kind of reminded me of fluctuations, all these nice colors of the boats. They're sort of in my head somehow like this product state of these fluctuations. It's kind of a dorky or nerdy joke. But,
so we will surely get you back. There are so many interesting things going on at Mad Science, including something called the Quantum Science Center, where you have young visitors spending few months with us. So I'm sure you will come and we'll sit on the boat and take a photograph also.
So I'm sure I'm missing out on a lot of nice conversations.
Right.
I tell my friends Bob Leshore, and I wish I could be there with everybody.
So thank you very much. So we'll get back to you officially with the cancellation charges and other things.
It came today, so I did. But so.
Okay. Thank you very much. Goodbye. So good night, and so we will communicate with you. So I will get out of Skype now. Bye. So we'll have tea and then come back at 11:30.